Hey everybody, it's Ripley back again. Today we're going to talk about volume of solids using shells, a different method. Now, the reason we need a different method is if you look at this problem, I've got f of x equals negative, I just wanted to build this out for you, negative quantity x minus 1 squared plus 1, which means we take an upside down parabola, we move it over 1, we move it up 1, we clean it up, and it's negative x squared plus 2x. Okay? So let's say that I wanted you to take this region right here. Whoa, that's not what I want, right? With the wrong end of the stylus. I wanted you to take the region bounded by the curve and the x-axis, this guy in here, make my little pretty thing, and I wanted you to go around the y-axis. And you're like, Ripley, that's no problem. That's the easiest. There's a hole between the action and the axis of rotation, and when I go to build my, wait a sec, this thing's not a function of, what the heck? How in God's name am I going to be able to do that? I can't draw a slice of action that is perpendicular to the axis of rotation. Whatever will I do? Well, I'm about to show you. So what we're going to do is, clearly I can't draw a horizontal slice of action. So what I'm going to do is I'm going to draw a vertical slice of action. All right? And this vertical, let's put a little x down here. And this vertical slice of action has a thickness of delta x, which is important because it tells us everything we need to know. I know that this curve passes through 0, 0, and then over here at 2, 0, and life is easy that way. But you say, I can't use discs or washers. Well, you're right. What you're going to use is shells. Okay, now any attempt that I would have, that I would try at sketching what's happening here would just be paltry. So what I'm going to do is I'm going to defer to our good friend Wolfram. They're so delightful. Okay, now look, this is kind of a curve that looks pretty akin to what I just drew. All right, you can tell here I've got my x-axis, my y-axis, and then I've got my depth into 3 dimensions. Now watch this. This is pretty cool. These are each slices of action. In my case, I had numbered down to 1. I don't like it with, I mean, look at this. This is awful. Let's give you a little something to look at. All right, you ready? What we're going to do is we're going to sweep this thing through 360 degrees. Well, in this case, we're only going through pi halves, or excuse me, through pi as opposed to 2 pi. Now, what does that make? What can you tell that this makes? Well, if you look, like this little slice of action right here, as it passes through, I want this thing to go, I want this to go through, I want to go through 2 pi. What the heck? Let's just go 6.28. Okay. And then, okay, yeah. Now let's see if it'll let me do it. Oh, is it going to let me do it? Nope. It won't let me do it, will it? Let's go plus. No. Oh, look at that. It's got a little graphic to it. All right, doesn't matter. So what? We'll just be able to go through pi. What you'll notice is that each one of these little slices of actions, as it carves through, in this case, pi, it's cutting out part of what looks kind of like a tuna fish can with the top and the bottom cut off. Well, that's what we refer to as a shell. Don't worry about these lines on here. They're like gradient lines. But as this guy passes through, what we end up with is shells. Now, wait, let's see if we can look at that. That's pretty fun. Let's do this. Hold on, let me drag this thing back. Well, let's have a little fun with it. Oh, apparently it won't let me do it. That's too bad. So as it swooshes through, in this case, 180 degrees, what you get is you get a series of cylindrical shells. Now, let me go back to this, because this is kind of important. The way that I think about this is like the Russian nesting dolls. I forget what they're called. I have students that could tell me, I'm sure. But remember, you know how a Russian nesting doll works, right? You got a big one, you open it up, there's a little one inside, you open that one up, you got a little one inside. Well, it works the same way, except think of them as like different tuna fish cans of different radii and different heights. So you end up with these guys all being stacked in on each other. And then if I let the number of them go to infinity, I end up with a volume that looks like that. Now it's definitely a bummer that they only let us go through 180, but I think that you'll get the idea. Now, so let's take one of these shells that happens when I take this little chunk, like this side right here. I'm going to take this side of my slice of action and run it through 360 degrees, right? This thing is still going to be f of x sub I, and then I'm just passing it through 360 degrees. And this just becomes what? What would the surface area of this thing be? It's the surface area of a cylinder, which is 2 pi r, the circumference of the base, times the height, right? So this would be 2 pi r times h, which in this case is 2 pi r times f of x sub I. Now, what's this r? Well, remember, this is delta x, which implies we need, everything has to be in terms of x. Can't have any y's. And I know the distance between the y-axis and the slice of action is x, right? It varies. As this slice of action moves through my region, this is always going to be x distance away from the y-axis. So this can be written as 2 pi x sub I should write that as x sub I, times f of x sub I. If I want the volume, what would the volume be? The volume of that IFB. How do I make a volume? Well, I add a thickness to it, right? I add a thickness to it, and then I run that thickness through 360 degrees with it. So how do I add that thickness? Where does the thickness come from in this little graphic? Well, it should be pretty easy right now to see that that's 2 pi x sub I times f of x sub I times delta x. If I want the overall volume, volume is going to be same as before. Where is the action taking place from and to? We got the integral from 0 to 2. We got a constant, so we might as well throw that thing out in front. Notice it's 2 pi, not pi. Students love to get confused and write pi thinking that, well, they're thinking they're using shells, but then they just brain cramp and do 2 pi instead. And this just becomes x times negative x squared plus 2x dx. Delta x becomes dx. All right, check this one out. You'll like this. How's about, let's go around x equals negative 2. Okay, I'll put it over here. Same function, only this time we're going around x equals negative 2. Okay, so what's it going to be? It's going to be volume. I'm going to have 2 pi times the integral from 0 to 2. That never changes because that's where the action is taking place from and to. But look, the only thing that's going to change, I know the distance from here to here is always x sub I. I know the distance from here to here is always positive 2. Be careful, right? So the distance from the axis of rotation out to the action is always going to be x plus 2 instead, times negative x squared plus 2x dx. Now, I don't know if you remember from last lesson, but I said we've got when we want to use discs or shells, we need to draw a slice of action that is perpendicular to the axis of rotation. Oh, wait for it. Strap yourselves in. It's coming. What does my action need to look like if I'm going around like in this case, I'm going around a vertical axis? What must my action be? It has to be paracellular. Woo! It's parashell. Ha! See, it's parashell. If we go back to here, whoa, if we go, get out of here. If we go back to here, remember not here. All of our slices of action were, like in this case, this was perpendicular to vertical lines, right? This was perpendicular to the y-axis. Yeah. Sorry, I'm just, I'm here to make your days a little brighter. That's what I do. All right, how about if we go around x equals 5? Now, the only thing that changes, this is what's so cool about this. So this is x equals 5. All right, volume is equal to 2 pi. Where's the action taking place from and to? But Ripley, we're going around x equals 5. Who cares? My action takes place from 0 to 2. Everything else adjusts. So from 0 to 2. Now, again, the distance from the y-axis to the slice of action is always x sub I, right? However, I need this radius. I need this guy. So if this is always x sub I, and this is always 5, the distance from here to here is always 5, then what's this going to be? Well, it should be pretty easy. It's just going to be 5 minus x times negative x squared plus 2x dx. And we're done. Now, can I go around either of these vertical axes using discs or washers? Again, no. And notice the color of my pen. If I try to draw a slice of action, I don't have a function. This is not I can't draw a function of y. So I'm screwed. All right. Shells is awesome. Shells, I prefer shells to discs because they don't have to do as much work as far as squaring and then worrying about things algebraically. But it's up to you. You should be able to think about this. Could we use both shells and washers? Oh, yeah. Let's try that. Okay. I'm not going to drive you guys too crazy here. What do I want to do? All right, so if I want to do this with shells, ooh, it's in red, that's a little scary. And I want to go around x equals -1. Let's do this guy, but I'm going to do it with shells. Okay, we're going to go around x equals -1. Now I know I'm going to change some stuff. I'm going around x equals -1. Here is my slice of action. This is a delta x, so everything's going to be in terms of x, right? I know that distance is always going to be x sub I. I know that distance is always going to be 1. So this is going to be 2 pi times the integral. Action's taking place from 0 to 2. That's weird. Again, the radius from the axis of rotation to the action is going to be 1 plus x. And then the height of this guy is going to be, what did we have? We had 2x minus x squared. And then I've got my dx. Likewise, I guess this is kind of the same thing that we did before. The only thing that's going to happen, x equals 5. I'm going to have 2 pi. These are volumes, by the way. By the way, these two volumes had better be exactly the same because they're describing the exact same thing. So I've got 2 pi integral 0 to 2. It's going to be 5 minus x, and then times 2x minus x squared dx. That's kind of cool. Nothing to it. Ooh, what if I wanted to go around the x-axis with shells? This is a fun one. Now look, if I'm going to go around the x-axis with shells, my slice of action, see this blue slice of action, needs to be parashell to the x-axis. So this is going to be a delta y. This is getting hard to read, but that's okay. Let me turn this back into blue. Back in blue. Sorry, that was stupid. And this distance is going to be y sub I, right? This is crazy. This is going to be volume equals 2 pi times the integral. Now this time, since this is a delta y, this slice of action is parashell to the axis of rotation. I'm going from 0 to 4, not 0 to 2. And then my distance, my radius, remember it's 2 pi rh, is going to be just y. And then my height is going to be this curve as a function of y minus this curve as a function of y, which is root y minus y halves dy. And I'm done. Nothing to it. Okay. That was a little bit kind of rushy through as I did these other problems, but just play with it. Just play with it. Then use your calculator to double check to make sure that the volumes are the same. They have to be the same. Whether I go around the x-axis with discs or washers, in this case it would be washers because there's a hole between the action and the axis of rotation, or with shells, notice parashellular as opposed to perpendicular, they better end up with the same volume. All right, I hope that was helpful. It was a little bit fun. I'll see you in the next lesson. We're starting to get towards the end of the curriculum here. It's kind of fun. I'll talk to you later.